Okay, let's talk about the wave nature of light. Now, light is also called electromagnetic radiation. Okay, but light's the more generic term. Sometimes people use light only to refer to visible light, but we'll use that term for all of electromagnetic radiation. And what electromagnetic radiation is a form of radiant energy. Okay, so it is another form of energy. Um, it's energy that travels as oscillating waves. Um, really, it's an electric field and a magnetic field that travel perpendicularly through space, and they move at the speed of light. Now, you don't really have to understand what the heck that means, that it's an electric field and a magnetic field, but that's where that name is coming from. You do need to just be familiar with the term electromagnetic radiation, and that basically that's describing light, or it's another term for light, and that it is radiant energy that moves at the speed of light. And so we will utilize the speed of light to do some calculations associated with light. Um, but there are many forms. So even though a lot of times people just think it's visible light, there are several other forms of electromagnetic radiation that are encompassed by that term, or even encompassed by the general term light. Okay, we can also have gamma rays, X-rays, ultraviolet light. Those are all higher energy forms of light than visible light. There's also infrared light, microwaves, and radio waves. Those are all forms of electromagnetic radiation. Those three are actually lower energy than visible light. So we kind of have those main 7 categorizations of electromagnetic radiation. Okay, and those all have kind of different characteristics, um, different uses, and so that's why they have different names. And we'll look a little bit into the different ages that they fall in. And so this diagram actually gives you a little bit of the information about wavelength and frequency of different types of electromagnetic radiation. You don't have to memorize that information, but it's just showing you that whether you're talking about gamma rays, X-rays, ultraviolet, visible, and so on, you're in a different wavelength region, or you're in a different frequency region of the electromagnetic radiation scale. Okay, so all those different ranges have different names. Okay, and it's based on kind of the characteristics of how they interact with matter. Okay, so that's really why we're interested in light and chemistry, is because we utilize light to study matter and to manipulate matter. And sometimes even light is emitted then by things that happen with matter. So that's why we're kind of interested in understanding a little bit of the characteristics about electromagnetic radiation or light. So let's go into specifically the characteristics of waves, which apply to light. Okay, we're going to look at 2 characteristics of waves that apply to light. So I've got some pictures of waves down at the bottom, and they're labeled with one of the first characteristic that we're going to talk about, which is wavelength. Okay, and wavelength, when we use it in calculations, the symbol we use is lambda. Okay, so that's what I have there right next to wavelength. And what wavelength is the distance between 2 consecutive peaks or troughs, or really any like point within a wave. Okay, and so like on that first picture, we've got the wavelength shown based on different points in the wave. And so from the peaks, that's that first one at the high points, the distance from one high point to the next, that's a measure of the wavelength. Or if you go to the low points in the waves, from one low point to the next low point is a wavelength, or like I said, any other light point. There's that one in the middle showing some kind of middle point, but basically where that wave starts to repeat itself. So you start at one point and where it repeats that pattern is your next point in that wavelength measurement. So it is a length. So a wavelength does have length units. So any valid length unit, typically we use things like meters, centimeters, millimeters, micrometers, and so on. Although you could use things like inches, I guess, we just don't. And so we use metric units. And usually the wavelengths for light are going to be pretty small. Okay, so you don't generally need to use the large metric prefixes. Now, frequency is the other characteristic that we're interested in that helps us understand light better and quantify things related to light. And frequency we symbolize using the symbol nu, which basically looks like a V. Usually it's a little bit curved, or the one side of it is a little bit curved. But you can write it as a V if you want, or you can write it as an F. Some people do that. I'll use a nu. But what the frequency is the number of waves that pass a stationary point per unit time. And so you would have to think of it as if these waves were in motion, okay? But a little bit easier way for us to think of it in terms of the diagram is we could take in this given distance how many waves there are, and that would tell us about the frequency of that wave. The units of it are in inverse time units, meaning 1 over time. Usually it's in 1 over seconds or some scaling of that. So the unit would be 1/s or s to the -1, which is the same thing, which we actually call hertz. Okay, so hertz we would label, or we would abbreviate as Hz. Okay, so hertz is the normal measurement for frequency, and that can be added to metric prefixes. So we could have the prefix with hertz. So you can have things like kilohertz, megahertz, terahertz as frequency measurements. Okay, and so it's telling you how many waves pass a given point in a second. Okay, per second. But if we look at that second picture that I have here of waves, you can see, oh, excuse me, you can see two different waves, wave A on the top and wave B on the bottom. And so since we don't have this really in motion right now, we're just going to keep that fixed distance and consider that our time axis and count how many waves pass in that time frame. And you can see that first one, we've got the first, the wavelength marked there. And so this first distance, that would be one wave, okay? And then if we go from that peak to the next peak, that would be our second wave. So this is essentially, if this was 1 second, that time frame, this would be a 2 hertz wave, okay? Whereas this second one, we've got the first wave marked from peak to peak, so that's one wave. And then to this next peak, that would be the second wave. And then to the third peak, that would be my third wave. And then to the fourth peak, that would be my fourth. So this one really is a 4 hertz wave if that axis was designated as 1 second, okay, if that was the time frame that was going on. Okay, to give you a general idea. And the nice thing about looking at kind of those two waves and comparing those frequencies is then if you compare the wavelengths, look at the relationship between those. When you have a longer wavelength like you do in wave A, you have a lower frequency. okay? Whereas when you have that shorter wavelength in wave B, you have more waves that can pass in a given time, so you have a higher frequency. And that's the next point I want to make. That's a really important relationship between wavelength and frequency. Wavelength and frequency are always inversely proportional, okay? Meaning the higher one is, the lower the other is, okay? So the higher the frequency, the shorter the wavelength, or the longer the wavelength, the lower the frequency. That's always true. But then one other characteristics of waves that's important for us to think about, oh, I guess I have another example here for you guys. I forgot I put that there. I've got an example of comparison between an IR laser and a green laser. So an IR laser puts out light with a wavelength of 1,000 nanometers, or at least this particular one, because there's a whole range of wavelengths. But let's say we have one that has a wavelength of 1,000 nanometers. If that were the case, its frequency would be 3 times 10 to the 14th hertz, okay? Whereas a green laser with a wavelength of 500 nanometers would have a frequency of 6 times 10 to the 14th hertz. So notice how the wavelength is half as much in that case, and the frequency is double, okay? So the higher one is, the lower the other is. They're inversely proportional. So you've got to know that. But the other characteristic waves that's important for us to understand how it relates to wavelength and frequency is the speed, okay? So how fast that wave is traveling is going to be directly proportional to the wavelength and frequency, okay? So the higher the speed, the faster it's moving, the higher your wavelength and frequency are going to be, okay? Now for us, we're focused specifically on light waves, okay? We don't care about any other waves right now. So if you're focused on light waves, then everything's moving at the speed of light, okay? So you don't really have to worry about that factor changing things. The only things changing is wavelength and frequency. And you can relate those by using this relationship, C equals lambda nu, okay? Where C is the speed of light, okay? Now, if you were talking about some other type of wave, C would be swapped out for the speed of whatever wave you're talking about. But we're going to be talking about light, so that is always C, which is equal to 2.998 times 10 to the 8th meters per second, okay? So that number won't change. The wavelength is specific to whatever light you're talking about, and so is the frequency, okay? So the product of those always has to equal the speed of light. And so when one of them changes, the other has to change. And when one of them goes up, the other is going to go down, okay? So we're going to use that equation to do some calculations to convert between wavelengths and frequencies. So let's do these two examples. And so these are related to the wave properties of light, which are wavelength and frequency, okay? So here, a laser emits green light of 532 nanometers, and I want to know what is the frequency of this green light, okay? So what I have is a wavelength, right? That 532 is the wavelength. And how you would know that is, if it's not directly said that it's the wavelength, you should know that because of the unit. So it's a length unit, so it has to be the wavelength. And we want to know the frequency, so that's what we're looking for, okay? So we have the wavelength, we're looking for the frequency. Our equation is C equals lambda nu, okay? And C is equal to 2.998 times 10 to the 8th meters per second. And so we can solve for nu. If we just rearrange that equation, nu should be equal to C divided by lambda. And then we put our speed of light, 2.998 times 10 to the 8th meters per second over our wavelength, which is 532 nanometers. Okay, now when you look at this, you should pay attention to your units. And if you look at your units right now, things don't cancel. If we're looking for a frequency, it should come out in hertz or 1/seconds. But the problem right now is the meters and nanometers don't cancel. So either before you plug in those nanometers, you need to convert them to meters, or you can do it all in one. I'm going to go ahead, since I already wrote it down, I'm going to just add in my unit conversion to the bottom of that fraction. And so I have nanometers. I want to cancel nanometers, so I'm going to divide by nanometers. I want to go to meters, so I'm going to put meters on the top of the fraction. And 1 meter contains 10 to the, well, it's milli, micro, nano, pico. That's 36912. So milli, micro, nano. Nano's the third one, so it's 10 to the 9th. Okay. And so that's going to cancel my nanometers. It's going to cancel meters and give me 1/seconds or hertz. So now I just need to type it in the calculator. So I take 2.998 times 10 to the 8th. I divide that by 532. And then I actually multiply it by 10 to the 9th, because that 10 to the 9th is on the bottom of the bottom. So it flips to the top. So I multiply by 10 to the 9th, or 1 times 10 to the 9th. And then I'm going to round to 3 sig figs because of that 532. So I get 5.64 times 10 to the 14th hertz. Or you could write it as 1/seconds if you prefer. Okay, so that would be my frequency. And then the next one, what is the wavelength in nanometers of light that has a frequency of 8.50 times 10 to the 14th hertz? So here I want wavelength, and I have the frequency of 8.50 times 10 to the 14th hertz, and I still have the speed of light's the same and the equation's the same, but now I'm going to rearrange that C equals lambda nu. I'm going to rearrange it and solve it for lambda, so that would be C over nu. So if I do that, 2.998 times 10 to the 8th meters per second divided by 8.50 times 10 to the 14th hertz. And hertz is the same as 1/seconds. So if it helps you, you can swap that out. Because what's going to happen is that 1/seconds cancels with the 1/seconds on the top. Okay. And so this value, when you type this in, this is going to come out in meters. So 2.998 times 10 to the 8th divided by 8.50 times 10 to the 14th. Okay. Now, if you're using the scientific notation button on your calculator, that's going to make this a lot easier. If not, you need to use parentheses around that scientific notation when you divide. So this comes out to 3.53 times 10 to the, let's see, 1, 2, 3, 6, 7, to the -7th meters. Okay, we want it in nanometers though. So I need to take that and convert. So let me, since I don't have a lot of space, I'll change colors. So hopefully get too confused here. 3.53 times 10 to the -7th meters. And I want to get rid of meters and I want to go to nanometers. 1 meter is 10 to the 9th nanometers. So the meters are going to cancel. And so if I multiply by 1 times 10 to the 9th, so times 1 times 10 to the 9th, that's going to give me, which should make sense, you can do your exponents in your head, It's 353 nanometers. Okay, so that is our wavelength. Okay, so it's a pretty basic equation. You just need to know one thing. You either need to know wavelength or frequency, and you can get the other, okay? Because the speed of light is constant. You just have to watch your units. It may be easiest always to either convert your wavelengths to meters or your frequencies to hertz before you plug them in. And then what comes out is either going to be meters or hertz. And then you can convert to the unit that you want afterwards. Or you can do it all in one step. It's up to you.